Hey everyone! Today we're going to dive into one of the most powerful and honestly elegant tools in all of calculus, Lagrange multipliers. It's a method for finding the absolute best, the maximum or minimum result, but with a catch. You have to follow certain rules. So, to get our heads around this, let's start with a really simple analogy. Imagine you're on a huge mountain and your goal is to get to the highest point. Easy enough, right? But what if you're not allowed to go just anywhere? What if you have to stick to a very specific winding trail? All of a sudden, it's a completely different problem. And this quote right here, this is the absolute heart of it. The whole mountain, that represents all the possible values of some function. Let's call it f of x, y. The trail, that's our constraint, a rule we have to follow, like g of xy equals k. So our job isn't to find the peak of the whole mountain, but just the highest point we can possibly reach while staying on that trail. And yeah, this process has a formal name. It's called constrained optimization. It's really the art of finding the very best solution when you don't have infinite freedom. And this stuff shows up absolutely everywhere, from designing the most efficient engine to planning an economic budget, where you're always working with limited resources. Okay, so this sounds tricky. I mean, where do you even start? Well, this is where the genius of a mathematician named Joseph Louis Lagrange comes into play. He had this just stunningly simple geometric insight that basically cracks the whole problem wide open. And this is it. This is the big aha moment. So remember the gradient of a function. It always points in the direction of the steepest, fastest climb. Lagrange realized that at the highest point you can possibly get to on the trail, the direction of your steepest climb on the mountain and the direction of the trail's boundary, they have to be perfectly parallel. They have to line up. That one geometric idea is the key to everything. So that's a really cool idea. But how do we turn a geometric insight into a practical tool that we can actually use to solve problems? Well, that's where the formal Lagrange multiplier method comes in. That entire beautiful geometric concept is captured in this one simple, powerful equation. That little upside-down triangle, nabla, just represents the gradient. So all this equation is saying is that the gradient of our function f is just a scaled version of the gradient of our constraint g. And that Greek letter lambda, that's our multiplier. It's really just a number, a constant, that stretches or shrinks one vector to prove that it's parallel to the other one. And what's great is that this equation gives us a clear recipe to follow every single time. Step 1, just calculate the gradients for your function and your constraint. Step 2, use the formula to set them parallel with lambda, which creates a system of equations. And step 3, you just solve that system to find your optimal points. It's a roadmap that works every time. You know, theory is one thing, but the absolute best way to really get this is to see it work. So let's put this method to the test with a few classic examples that you definitely run into in a university calculus course. Let's kick things off with this one. We want to maximize the function f of xy equals xy. But we have a rule. We're constrained to only the points on a circle with a radius of the square root of 8. So you can think of that circle as our trail. We need to find the exact point on that circle where the product of x and y is the biggest it can be. Okay, so first things first, we find our gradients. We just take the partial derivatives. For our function f, the gradient is negative y comma x. For our constraint g, the circle, the gradient is 2x comma 2y. Now we just set them parallel using our formula. That gives us two equations to work with. Y equals lambda times 2x and x equals lambda times 2y. And there it is. That's the system we need to solve. Now, if you start playing around with those two equations, maybe solve for lambda in both and set them equal, or substitute one into the other, you'll uncover this really simple hidden relationship. X squared must equal y squared. That little insight is the key that just cracks this whole problem open. So we take that new piece of information and we plug it back into our original constraint. X squared plus y squared equals 8. If we replace y squared with x squared, we get 2x squared equals 8, which means x squared equals 4. So x can be positive or negative 2. And since x squared equals y squared, y can also be positive or negative 2. Now, to maximize the product xy, we want both to be positive. So we choose the point 2, 2, which gives us our final answer, 4. All right, let's try another one. This is a classic distance minimization problem. Our trail, our constraint, is the hyperbola xy equals 1. And our goal is to find the point on that curve that's the closest to the center, to the origin, 0, 0. So what function are we trying to minimize here? So here's a little pro tip for any calculus student. Minimizing distance is exactly the same as minimizing the square of the distance. So we're going to optimize the function f of xy equals x squared plus y squared. Trust me, this trick lets you avoid a ton of messy square roots. So we set up our Lagrange system again, and we get 2x equals lambda times y and 2y equals lambda times x. And again, after a little bit of algebra, we find that same relationship. X squared has to equal y squared. But we also know from our constraint that xy equals 1, which means x and y have to have the same sign, either both positive or both negative. That leaves us with only two possible points that are closest to the origin, 1, 1 and -1, -1. Okay, let's take this up a notch and apply the method in 3 dimensions. Imagine we want to build the biggest possible box, meaning we want to maximize the volume, V equals XYZ. But we only have a fixed amount of material to work with, say a surface area of 12. Now, when you actually set up the gradient equations for this problem, you'll notice something kind of beautiful. The equations you get for x, for y, and for z, they look almost identical. They're symmetric, and we can use this symmetry as a really powerful logical shortcut. Think about it, right? The problem treats length, width, and height, x, y, and z, in exactly the same way. So it makes sense that the best, most optimal solution must also treat them in the same way. There's just no reason for one dimension to be longer than the others. This powerful symmetry argument tells us, without even finishing the algebra, that the optimal shape must be a cube, where x equals y equals z. And with that amazing insight, that the box has to be a cube, the problem becomes super simple. We just plug x equals y equals z back into our surface area constraint, solve for x, and find that the maximum possible volume is 2 times the square root of 2. The method literally found the most efficient shape for us. So, after all that, what's the big idea? What's the main takeaway from all this? Let's just quickly recap the key points. I want you to remember 3 things. First, Lagrange multipliers are your go-to tool for any optimization problem that has rules or constraints. Second, the reason it works isn't magic. It's that simple, beautiful geometric idea about parallel gradients. And third, the method itself is this super versatile recipe that you can apply to problems in 2 dimensions, 3 dimensions, or even more. You know, this technique isn't just something for a textbook. It's used in economics to model how people make choices, in engineering to design the strongest bridges with the least amount of material, and even in machine learning. So the real question I want to leave you with is this. Now that you understand the logic, what problems in your world can you optimize?